Hello friends, and welcome back to another puzzle. We're at 7 of 150. Christmas tree is starting to look quite nice. We're still a long ways away from day 25. But let's dig into day number 7. Day 7, some assembly required. This year, Santa brought little Bobby tables, a set of wires and bitwise logic gates. It's awesome. Bobby tables actually made famous by XKCD. I'll put a link here somewhere to the comic. Unfortunately, the little Bobby is a little under the recommended age range and he needs help assembling the circuit. Each wire has an identifier, some lowercase letters, and can carry a 16-bit signal. A number from 0 to 65,535. A signal is provided to each wire by a gate, another wire, or a specific value. Each wire can only get a signal from one source but can provide its signal to multiple destinations. A gate provides no signal until all of its inputs have a signal. Alright. The included instruction booklet describes how to connect the parts together. X and Y becomes Z, means to connect the wires X and Y to an AND gate, and then connect its output to the wire Z. There's some examples. Other possible gates include OR, bitwise OR, the right shift. If for some reason you'd like to emulate the circuit instead, almost all programming languages provide operators for these gates, right? Yeah. For example, there is a simple circuit 1, 2, 3 to X, 4, 5, 6 to Y. X and Y becomes D, X or Y becomes E, X left shift 2 becomes F, Y right shift 2 becomes G, not X becomes H, and not Y becomes I. After it's run, these are the signals on the wires. Alright, we can use that as our test case. That's very helpful. In Little Bobby's Kit instructions booklet, provided as your puzzle input, what signal is ultimately provided to wire A? Let's take a look at our input. Alright, the input is quite significant. Too much for us to just calculate what it is. Alright, so how do we solve this? When looking at the input, you notice that it's not in sequence, so it's quite hard to just follow the instructions and then just brute force it. So we'll just create some form of circuit, I guess. We have wires, we have gates, we have binary operations, or bitwise operations, I should say. Let's take an example of our previous challenge, puzzle 6. We parsed instructions and we applied those to the grid. Let's do the same thing for this challenge. Just create an enum for the operation. So the int binary operator will allow us to make a function that takes two integers and apply some operation to it, which will be our bitwise operation. And we'll need a constructor, of course. Now we need to create some enums that actually do our bitwise operations. So for each operation that is created using these enums, they will take the X and Y, so the two integer values, and then we can use the inline syntax to actually perform our operation. So in this case, the AND will be the X ampersand, which is the bitwise AND in Java, Y. Bitwise OR will do the NOT, which I had to look up, but it's basically not X and then masked with the 4-byte Fs, which will make it a 16-bit integer. Right shift will just be the X right shifted to Y, same with the X left shifted to Y, and then I create the special one, assign X, which is the value that is directly connected to a wire, which we'll call an assignment, and then it will take the X value and just return that. All these operations are performed on a thing called a wire. So let's create an encapsulating class for that can hold the name and the value, and then the gate will actually be the thing that does the operation. So we create a small class which holds the name and the value, and we can use Lombok to actually do all the heavy lifting, or the boilerplate for us. So we need at least one all-args constructor which takes the name and the value. We also want one that just does the name, I guess, because not everything has a value at a certain point. So we'll just do a required args constructor, but then we need to say that the name is actually non-null. It will not be valid for it to have a null value. And for our debugging, we'll use the toString, and then because we're probably going to put them in a list or a map of some sorts, we'll give it an equals and hash code as well. This allows us to put objects in containers or collections, and then it will be compared not on the object but on the contents of the object while putting them in and searching. And wires are connected to gates, and gates actually map the wires to the operation. I guess the same conditions can apply to the gate. We'll have the all-args constructor, we'll have the required args constructor, toString and equals and hash code. And the only thing that is probably required when we start the gate is to have a name so that we can find it. And it will have connection to the left wire, the right wire, and the result wire. And the result wire at its turn can be connected to many other gates. Important thing here is, of course, the operation that we need to apply to the gate. The gates require a name. I'm thinking to use the name of the result wire, so the wire to which the output of the gate connects to, because there's only one. So that would be a unique name. And we'll create two maps, one that holds the wires and one that holds the gates. I don't think we can construct the object graph in a neat way because it's all out of sync within the input. When we get values from these maps, we have to take into account the default operations. So if we're looking for a wire that is not there, it should be created, but some wires can have inputs which are digits, which is the value that is sent to that wire. So it could also be a digit which then becomes the value as well. So we have get wire, and all it does is return a wire. So if we pass a name to the get wire function, if it is a digit, it should create a nameless wire with the value of the digit. It is not a digit, it should create a new wire with the name. But how do we know that the name of the thing is actually a digit? Well, we only need to take a look at the first character, I guess, because if it is a digit, it will be the value of the wire. So it doesn't matter how long the number is, the first character will be a number. You can basically just create that function by using character.isDigit, and we'll take the character at the very starting point of the string and then return true if it is a digit. So now we'll have a nameless wire which has a value, or we'll get a wire from the map of wires, and if it does not exist, it will create a new wire with that name. I don't think it's relevant for the gates, but I've just copied over the same logic for the gate. So we have wires, we have gates, we have operations. So now we can basically construct the circuit, and then we have to figure out how to fire off events on the circuit. So let's just take the input, which is our list of strings, and then for each input we'll split the string on spaces. Basically the same thing we did at puzzle 6. We know we're going to need a left, right, and result wire as well as the operation itself. And now we can basically take a look at the length of the operations, or actually the length of the instructions in the string. Either it will be 3, 4, or 5 positions long. So we'll take our switch, and the first case will be 3 positions long. It will be an assignment, so basically a number leading to a wire, or a wire leading to a wire, or well, that's it, I guess. So the get operation, get wire, will when it's a number, it will just get a nameless wire with a value assigned to it, or else it will get the current wire from the map itself. And the operation, it will be an assignment, so we'll basically assign a value to this wire. So in case there's 4 elements, it will actually be a NOT. So NOT will be NOT X becomes wire Y. Same logic applies. We get the left wire, we get the result wire, which in this case is actually instruction 1 and instruction 3 within the array. And then we'll assign operation NOT. And then finally we have case number 5, of case of the length of 5, in which we have a left wire, a right wire, an operation, and then a result wire, which probably be the most common case, I guess. And we can also make a default case in case we find some edge case that we have not taken into account at this moment. So let's grab a gate using our getGate function. This should actually always return a new gate. I'm thinking about it now, but let's keep the function as this. And we'll hook up this gate to the wires and operation that we already defined. And then we'll put the gate back into the gates map with the name of the result wire, which should be unique, as a wire will have 1 result. And then we need to store our wires itself as well, and just to have them. We need a function for that. So create a function store wires, which takes 1 or many wires. So we'll use the varargs function within Java, which means that we can have an unlimited number of wires passed to store wires. We'll loop over them, and if it's not null, we'll just put them into the map with the name. Cool, so we have built our circuit. Now we need to fire the circuit off and basically give a signal on each wire. Let's first update our part1 function to, so we'll create circuit on input, which will be our circuit, and then we'll have the function firewire actually activate the wire and then travel down the circuit in order to make sure that all the circuits that, or all the gates that are required are actually have a signal that can feed our A, for which we need to have the value. So let's take a look at what it means to have a fire of the wire. The fire of the wire, there we go. So we have our function fire wire. We need the gate that we're looking at, and a gate is named after the result wire. So this is the gate that connects to the result wire A and has the input wires on the other side, on left and right. As long as the result wire's value equals -1, which is the default value, we'll call the fire function on the gate, which we have not made yet, but we will make it, which means that it will keep firing until all the signals are activated. So we'll do that on the gate, as the gate has the operation. A gate will only perform its own operation when both the left and the right wire have a signal. So we need to check if both wires actually have a signal, and then we can do our own operation, which will allow us to recurse until all the wires have a signal. So what does it mean to have a value on a wire? So we'll have a boolean that says it's valid. If the left part is not null and it has a value of -1, which is the default value, then the left part is not valid yet. The same with the right. I will return that. So unless both left and right are either null or have a value, it will not be valid. But when it is valid, we need to actually perform the operation that is tied to this gate, either the AND or the left shift, right shift, or the assignment itself. And what does it mean to do a perform of this gate? It means that the operation, the binary int operator that we hooked up to it, gets called with the values of both left and right. So unless the operation is null, because it can be null, we're a little bit defensive here, the result value will actually be the apply as int, so we'll have an int value. If left is not null, it will be left's value, or else it will be 0. If right's not null, then it will be right's value or 0. 0 probably means do nothing. And else we'll take the value of the wires and apply that by using the op function that we already connected. So this is only the case when the wires are both valid, but they need to become valid first. So to do that, we will fire each individual wire. So we'll start at left. So if the left wire is not null and the name does not equal empty, which is numeric wires that we created, we'll get the gate. So there will be actually a gate connected to it on left's name, and then we'll fire off that gate. And then it will do the same for itself, and then it continues up the circuit until it hits the endpoint, where there's only a assignment of a value to a wire, which is not a gate in itself. We'll do the same for the right wire, and so both wires will be connected. They will have a signal, and when both have a signal, the current gate that we're in will actually be performed, and so it will trickle through the entire circuit. We should be able to run our circuit now. Let's give it a try. According to our test case, the value of A would be 46,065. Let's see if our value is correct. Yes, our circuit was successful. Let's take a look what Santa has in store for number 2. Part 2. Now take the signal you got on wire A, override wire B to that signal, and reset the other wires, including wire A. What new signal is ultimately provided to wire A? Okay, so we need to build our circuit, set the value of B to that of A, and then recalculate everything again. Let's copy over everything from part 1, and instead of returning the value of A, we'll catch that value. One thing to note, in my test case, I reuse the object for the day, which normally is not a problem, but now we have some state that we have to manage. So at the time that we run part 2, the values of part 1 will be in there as well. So we need to clear the wires and the gates. And once we have the value of A, we'll do the same thing again. And we'll rerun the gate itself, and in between, or we can just take this one. And in between, we need to take the value of A and set it to B. And we can do that by taking the gate and then setting the result wire of B to that value. So we'll get gate B. That will actually be the one that is built within the circuit. I'm doing this. Oh, we should create the circuit. Yeah, right. All right, I'm back. There we go. So to recap, in part 2, we clear what we did in part 1. We create a new circuit. We take the value that we get from firing wire A. Then we'll clear everything, rebuild the circuit again, so it's neat without any values. Then we'll take the gate that is stored as B, which is the name of the result wire. So that will be probably a gate that has an assignment of some value to B. We reset the value of B to the value that we got from A, and then we'll set the operation of gate B to null, so there will be no thing going on when we hit perform. And then we see what wire A has for value when we fire it up again. Let's give it a try. We hit the test case and the value now is 14,134. Let's give it a try, see if it's right. Yes, we did it. Our circuit worked. You see, as we're progressing, we're now at day 7. The puzzles get a little harder, a little more stuff to do to solve them. Let's see what day 8 has in store for us. See you then.